good afternoon everyone. I'm Doran Songcados, and my task this afternoon is to discuss to you my final report number 2 that were chapter 3 permutation groups. So, first let us define what is permutation. So, as I have researched, permutation is a mathematical technique that determines the number of a possible arrangement in a set when the order of the arrangement matters. So, mao to siya ang meaning sa permutation. So now, let us define what is permutation group. So, permutation group is a group whose elements are permutation of a given set M and whose group operation in G which are thought of as bijective. When we say bijective, it is a function between the elements of two sets where each element of one set is paired with exactly one element of the other set. So, bijective functions from the set M itself. It means that it is a subgroup of a symmetric group. So, symmetric group is a set of all bijectives from the set to itself with composition of functions as group action. So, mo na siya ang meaning sa permutation group. Now, let us define permutation group with the definition 3.1.1. A group X be a non-empty set. A permutation phi of X is a one-to-one function from X onto X. Definition 3.1.2. A group of G and operation product is called a permutation group on a non-empty set X if the elements of G are permutation of X and the operation is the composition of two functions. So, example 3.1.3. Let X be any non-empty set and S of n be the set of all one-to-one functions from X onto X. As defined in example 2.1.9, then S sub n and 0 is a group we have shown in example 2.1.9 where 0 is the composition of functions. Hence, quantity of Sn and 0 is a permutation group. So now let us know the theorem 3.1.8, the basic properties of S sub n. Number 1, S of n and 0 is a group for any positive integer n is greater than or equal to 1. Number 2, if n is greater than or equal to 3, then quantity of S sub n and 0 is non-commutative. 3, S sub n is equal to n factorial. So, proof. Number 1, we have already noted that the set of all one-one functions of any non-empty set onto itself forms a group under composition of functions in example 2.1.9. Thus, quantity of Sn and 0 is a group for any positive integer n is greater than or equal to 1. Number 2, let n is greater than or equal to 3. Let alpha, beta, an element of S sub n be defined by alpha is equal to quantity of 1, 2, 2 and 3, 3 and 2, and 4 and 4, and beta is equal to 1 and 3, 2 and 2, 3 and 1, 4 and 4, up to n. So now, we will find the function composition of alpha and beta. So, in the book, alpha composition of beta is equal to 1, 2, 2, 3, 3, 1, 4, 4, up to n. And function composition of beta to alpha is equal to 1, 3, 2, 1, 3, 2, 4, 4, up to n. Number 3, thus, quantity of alpha composition to beta of 1 is equal to 2 and not equal to 3 is equal to quantity of beta function composition to alpha is of 1. Hence, alpha of beta is not equal to beta of alpha. And so, S of n is commutative. So, before we will continue to definition 3.1.9, I have here an example to really understand how to get the function composition of two different functions. So here is my example. Function f is equal to 1, 3, 2, 5, 3, 4, 4, 1, 5, 2. And then function of g is equal to 1, 3, 2, 1, 3, 5, 4, 2, and 5, 4. So first, let us define what is the function composition of f of g. So f of g of 1 is equal to f of 3. So f of 3 is equal to 4. So f of g of 1 is equal to f of 3 is equal to 4. So the output for number 1 is 4. Next, f of g of 2 is equal to f so continue. F of g of 2 is equal to f of 1 equal to 3, and so on. So the output for f of g, function composition of f of g is 4, 3, 2, 5. F of g of 5 is equal to f of 4 rather. So f of 4 na siya, guys. Equal to 4, 1. 1 is siya. So this process is what we call the cycle notation, wherein diba kani siya ang atong f of g of 1 muna siya is equal to 3 maps to 4. So muna siya, therefore nakakuha tag 4. Then kung moanhita diri sa ato ang f of g of 5 is equal to f of 4, so tanawon na to siya diri, damo ni siya ang g map ay 5 maps to 4 and then 4 maps to 1. Diba? Kung ibalik lang nimo siya, kung kani silang duha, ibalik lang nimo na siya, 1 maps to 3. So mo na siya ang gitawag na tog cycle notation. Ma-discuss na to na siya unya after ani nga example. So next, let us proceed to function composition of g of f. By the way, this upper part of the function composition of f of g is what we call input. Kani sila mo ni siya atong input. Then kani siya mo ni siya atong gitawag nga output. Sila mo ni siya output. Okay, let's continue. So g of f is equal g of f of same ra sila kanang given. G of f of 1 is equal to g of 3 is equal to 5. Next, g of f of 2 is equal to g of 5 equal to 4. Next, g of f of 3 is equal to G of 4 equal to 2. Next, G of F of 4 is equal to G of 1 equal to 3. Last, G of F of 5 is equal to G of 2 equal to 1. So, this, the result of function composition of F, G of F is 5, 4, 2, 3, and 1. So, this is a function composition of G of F. So definition 3.1.9. The group of S sub n 0 is called the symmetric group on Ln. So what I have said earlier, that symmetric group is a set of all bijection. So bijection between the function of two sets where each element is one set is paired by exactly one element of the other set. So consider the permutation pi is equal to quantity of 1 pi of 1 to pi of 2 up to n pi of n. If pi of I is equal to 1, then we drop the column 1 is a pi of 1. For example, alpha is equal to 1, 1, 2, 4, 3, 3, 4, 2 is denoted by 2 of 4, 4 of 2. So, the example of alpha 1, 1, 2, 4, 3, 3, and 4, 2, which is 2, 4, and 4, 2, it is what we call the cycle notation, wherein 2 maps to 4, 4 maps to 2, and then 2 maps to 4. So, nagbalik-balik lang siya. Muna siya gitawag og cycle notation. So, example 3.1.11. Using the cycle notation, we can write S is equal to the set of E, quantity of 1, 2, quantity of 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. We note some of properties of the group Sn of 0. 1. Sn, S sub n, 0 is a non-commutative group of order 6 by theorem 3.1.8. 2. Sn contains two elements of order 3. For 1, 2, 3 of 1, 2, 3 is equal to 1, 3, 2 and not equal to E. And 1, 2, 3 of 1, 2, 3 of 1, 2, 3 is equal to E. Hence, the order of 1, 2, 3 is 3. Similarly, the order of 1, 3, 2 is 3. The order of 1, 2, 1, 3, and 2, 3 is 2 since 1, 2 of 1, 2 is equal to E. 1, 3 of 1, 3 is equal to E and 2, 3 of 2, 3 is equal to E. Since balik-balik lang siya, muna siya is equal to E kay 1 ra na siya, ang value na siya ay 1. Ang ilang order kay sa isa ka quantity duha ra sila, tapos ibutig magamit ang cycle notation, magbalik-balik ra na siya ang result. So number 3, in Sn the product of distinct elements of order 2 is an element of order 3. 1 3 of 2 3 is equal to 1 2 3, 1 3 of 1 2 is equal to 1 2 3, 1 2 of 1 3 is equal to 1 3 2, 2 3 of 1 2 is equal to 1 3 2, and 1 3 of 2 3 is equal to 1 3 2, and 2 3 of 1 3 is equal to 1 2 3. Definition 3.1.12. Let alpha, beta an element of S. Then alpha and beta are called conjugate if there exists y such that y of alpha and y is equal to beta. Conjugate means the form by changing the sign between two terms in a binomial. So, for example, the conjugate of x plus y is x minus y. In other words, the two binomials are conjugate of each other. So, theorem 3.1.13, let pi is equal to I of sub 1, I of sub 2, up to I of sub n, an element of S of n by a cycle. Then, for all alpha, an element of S sub n rather. So, alpha of pi of alpha raised to negative 1 is equal to quantity of alpha of I sub 1, alpha I of sub 2, up to alpha I of sub I. Proof. Since alpha is an element of S sub n, alpha is a one-one mapping of Ln onto Ln. Thus, the elements of alpha of 1 up to alpha of n is an element of Ln are all distinct, and so Ln is equal to the set of alpha of 1, alpha of 2, to alpha of n. Let R be any integer such that 1 is less than or equal to R less than to 1. Then, quantity of alpha of pi of alpha raised to negative 1 of alpha of I sub R. So, muna siya guys. So, let's continue with example 3.1.17. Consider the permutation pi. So, guys, na-erase akong amot nga na naunsa na siya. Error na siya. So, consider the permutation pi is equal to 1, 6, 2, 3, 3, 5, 4, 2, 5, 4, 6, 7, 7, 1 on L of 7. Here, pi of 1 is equal to 6, pi of 1 is equal to pi of 6 is equal to 7, and pi of 1 is equal to pi of 7 is equal to 1. That is 1 to 6 to 7 to 1. Hence, notation is equal to 167 is a 3 cycle. Now, 2 is the first element of L7. Not appearing in 167. Also, pi of 2 is equal to 3 and pi of 2 is equal to pi of 3 equal to 5. Pi of 2 equal to pi of 5 equal to 4, and pi of 2 is equal to pi of 4 equal to 2. That is 2 to 3 to 5 to 4 and to 2. Hence, notation is equal to 2, 3, 5, 4 is a cycle of length 4. Now, notation and notation are disjoint, and pi is equal to omricon or notation function composition of notation. So, in a cycle notation, we can make any number of cycle. It's either 3, 2, 4, 5, depende sa ato So, let's continue with definition 3.1.20. Let pi, kuha na siya kay element of S sub n. If pi is a product of an even number of transposition, then pi is called an even permutation. Otherwise, pi is called an odd permutation. So, nakadepende ang ato ang permutation. It's either even or odd sa product sa transposition. So, corollary 3.1.21. Let pi 1, let pi an element of Sn be a k cycle, then pi is an even permutation if and only if k is odd. So, proof, let pi is equal to 1, 2, up to k. Then pi is equal to 1k of 1k minus 1 of up to function composition of 1, 2, etc. Pi is a product of k minus 1 transposition. If pi is an even permutation, k minus 1 is even, and so k is odd. On the other hand, if k is odd, then k negative 1 is even, and so pi is an even permutation. Okay. Let an denote the subset of S sub n of all even permutation n is greater than or equal to 2. So, theorem 3.1.22. For n greater than or equal to 2, the pair A sub n to 0 is a group called alternating group on Ln. Proof, since E is equal to pair of 1, 2 of pair of 1, 2, an element of E is an element of A, and thus A sub n is not equal to a null set. So, wala siya sulod. A product pi of pi is even if and only if pi and pi are both even or both odd by theorem 3.1.19. Therefore, A sub n is closed under 0. If pi is an element of an, then pi of pi to raise to negative 1 is equal to E, is even, and hence pi raised to negative 1 an element of A sub n. Hence, pair A sub n and 0 is a group. So, theorem 3.1.23. Every element in A sub n is a product of 3 cycles. N is greater than or equal to 3. Proof. Let pi an element of A sub n. Then, pi is equal to omicron of omicron up to of omicron, where omicron is a transposition 1. 1 is less than or equal to I, less than or equal to R, and R is even. Now, for A transposition, so guys, ako ang slides is na inana na siya, kaya transfer na ako siya phone, nag-send raman gyapon ko sa GC. So, let's continue. Ay, last day siya, guys. So, where M is even, and since one of I sub 1 of I sub 2 of 1 and I sub 2, it follows that pi is a product of 3 cycles. So, the highlight of this report is about the permutation, about the cycle notation, and if naamoy mga pangutana about sa cycle notation o sa permutation, you can ask me, and kung basin makaya ran ako siya answer. So, thank you and God bless.